Hello, everyone, and welcome to episode number 60 of the Hyperthesis. We have a very exciting guest for you today. So, to start, I'm Patrick.
I'm Pheely.
I'm Liam.
I'm Tahya.
So, as you heard, we have Tahya joining us today. So, we'll get into what she does in our main topic. But just as a quick introduction, we have Tahya Weiss-Gibbons, who completed her Bachelor's of Science from the University of Victoria in 2019, majoring in both physics and computer science. She worked at the Canadian Centre for Climate Modelling and Analysis during her undergraduate degree and continued working on short-lived climate forcers in the Arctic as a physical scientist until 2020. She completed her master's in 2022 at the University of Alberta, working under Dr. Paul Myers, with her thesis being titled Impacts of Runoff Forcing on the Arctic Ocean, Modeling Changes in Flow and Temperature. Currently, she is continuing to work towards her PhD at the University of Alberta and studies high-resolution coupled climate models in order to understand the Arctic climate change. So we'll be talking a lot about climate change and some modeling and the complexities behind that. But before we get into there, as an intro topic, if no one else has anything to say, I just want to quickly talk about what's known as environmental DNA. So this is something that a project of mine that's upcoming will be using, but I'm learning more and more about it, and it's becoming really cool. So environmental DNA is where we have essentially DNA that's found within an environment because it's shed off of skin or some sort of living tissue has been shed into the surrounding environment from organisms within the environment, and then we can collect that and figure out what has either passed through there or what's present.
I think you talked about this before at one point. I don't remember when, though.
Huh. Well, you're going to hear more about it.
Yeah, there was an episode. We had a whole conversation about this, or maybe it was like after an episode, and we just stuck around in the Discord call. I don't know. But we definitely had a conversation about this once because I kept asking like how much environmental DNA you'd find at like a bar at 2 a.m. or something. I don't remember.
Yes. So in this context, so I was at a conference not too long ago, and in this context, I want to talk about not in a bar situation or anything, which I'm sure would be very interesting, especially with like the molds and the people that are present. But at the conference I was at, there were a lot of biodiversity talks and how we can measure biodiversity. And there's this really cool project going on that is trying to measure biodiversity globally so that we can have a catalog of all the species that are present in the world by 2045. So this is a really cool project. The speaker was, very established in his field, but essentially this project is taking part in 3 different parts. The first 2 parts, the first part is fully completed. The second part is undergoing completion. And the third part will run from 2030 to 2045. And it's part of a project known as the Barcode of Life, or the International Barcode of Life. And essentially this is designed to try and figure out how many species there are and keep a catalog of them so that we can monitor their changes, which is extremely intense and super cool because it requires, their 2030 to 2045 mission will require about $800 million of funding to actually do it, which for an ecology kind of related project is a lot. For physics projects, not so much, or astronomy projects, because we have many billion-dollar projects that have gone on, like the Large Hadron Collider or James Webb Space Telescope. But it's just a very interesting concept, and they're seeing a lot of good results from the second phase so far.
Well, it's talking about like budgeting. I was gonna throw some shade to the dark matter people. It's like, maybe they're not gonna fight it as they're putting a lot of money into it. I think I talked to Liam a little bit about that. I saw that Roger Penrose talked about he's kind of against dark matter, doesn't believe that it exists, and it's pretty convincing argument. But hey, we'll see. I would love to be wrong.
I mean, I'm sure if they would love if you could throw some shade, because that might be dark matter in the shade. But yeah, no, it's just interesting where we have these massive global projects that have a pretty immediate effect on the world in which we live in, but they are not necessarily overseen, but they're underfunded for sure and struggle to get the necessary funding. Whereas thinking about these large collaborations, so like Snow Lab, for example, that was a large collaboration. It won the Nobel Prize in 2015, and that was quite an expensive project. They're looking at currently expanding the Large Hadron Collider, also a very big undertaking, but they're able to get the funding for that. Or another one is ITER, the fusion reactor being built in France. That's received like, I don't know how many billions in funding and has gone many years over schedule, but it's still receiving funding. It's still receiving excitement about it. Whereas projects like this are, again, where do you hear about it in the news aside from the doom and gloom kind of thing?
Well, yeah, we talked about it in our nuclear fusion episode with Edward Debit, which the tokamak in France that is building. So if you're interested, backlog and go listen to that episode. But yeah, I feel like the ecology surveys are a little more fluctuating, right? It's not like let's say you find new particles, it's there, it's not going to go anywhere. Well, I mean, it's going everywhere. But there's always constant stream of it. But maybe if we don't do some ecological surveys now, in a few years we might not be able to because they're all gone extinct, and it's really difficult to determine. Sometime I think I'll be talking a little bit in my story at the end about some of it, which I think some of you might find interesting, because when I read about it, I found it quite interesting.
Well then, I guess speaking about ecology and what we might lose and what's currently being lost and all that, let's move on to our main topic, which is featuring Tahya.
Hi.
So, Tahya, what do you do?
I basically run climate models in the Arctic, specifically focusing on Arctic oceanography. So looking at freshwater in the Arctic and freshwater changes, like as we warm up with climate change, we melt a bunch of ice, Greenland hydrological cycle, melts a bunch of permafrost. What does that do to the Arctic Ocean? What does that do to carbon sequestration? What does that do to circulation? Looking at those kind of processes, because the Arctic is very sensitive to climate change, more so than a lot of other places in the world.
So why is that? Why is it so sensitive? Is it because it's cold?
So it's called polar amplification, or Arctic amplification specifically. It's technically like a physical concept that you would see in both poles, but it really only has manifested so far in the Arctic, where the polar regions warm faster than the global mean. And by faster, I mean like the Arctic so far has been observed to warm 4 times faster than the rest of the globe. And this could mean for every 1 degree of warming in like global mean warming with climate change, you could get 4 to 7 degrees of warming in the Arctic. And it's to do from a lot of different processes, just like this heat transfer of like, we get a lot of excess heat from the sun at the equator, and then this heat is then transported northward and southward through current systems to kind of do with this imbalance. So you have this heat transfer going up. You also have like feedback effects of like, these are like the ice albedo feedback. You may have heard of this one, of where when you're melting a lot of ice, this ice is like white, so it reflects solar radiation back into the atmosphere. So if you have ice, it's cooler because it reflects that solar radiation back, and then you're able to keep cooler. So once you start melting it, you losing that albedo, you have more incoming solar radiation. This can then melt more ice, which is then lowering the albedo again. So then you have more incoming solar radiation. So it's kind of this like positive feedback effect of then you get a really fast warming like area.
I guess it's related to, let's say, if your roof in the winter is covered in snow, right? Your house will be colder because most of the energy from the sun is reflected away. Ah, that's interesting. So when you say climate model, what do you mean? What do you mean by model?
Yeah, like I mean like a numerical model. So we take physical, like your physical equations, your physical Navier-Stokes equation, momentum transfer equations, and you put them, you parameterize some aspects of them, and you run them on a grid. You chop up the Earth into a bunch of little squares of different sizes, and then you run that forward in time to see either understanding processes we don't have observations for, so understanding like we can't, the Earth is way too big to have an observation at every point. We have very few observations in some ways over long time periods. Or to figure out what's going to happen in the future. If you know the physical equations that are governing the system, and you know the forcing, i.e., you know, you can make an estimate of how much greenhouse gases are going in the atmosphere, you know the incoming solar radiation, you can then come up with an estimate of what's going to happen in the future in the climate as like a basic idea of them.
This is more but on the air, right? Is it not? So do you work also on like oceania at all, or like the model of currents and stuff, or both?
Yeah, so I specifically work on, we call them coupled ocean atmosphere climate models. So where you run an atmosphere component and then you run an ocean component. There's also, I've done also work on ocean only models or atmosphere only models where you have like kind of a simulated forced ocean or atmosphere, and then you just run the physical equations for one component of it. The general like components of a climate model are like your atmosphere model, your ocean, you could have a land surface model, you could have an ice sheet model, you could have sea ice models, you could have biogeochemistry in the water. So how much you include in climate models depends on your question and what you're trying to study and how much computing resources you have, because that's like a really big limit for us, because you could do a lot more if, you know, you had enough resources.
I'm so used to Navier-Stokes equation, like super simple, you know, it's like water or like air or maybe two fluids or something like that. But I'm so used to, you know, it's just like a simple, well, I say simple equation, a simple looking equation. And then maybe there's viscosity if you care about that. So like, what do these equations even look like? Because it's so much more complicated for the air in the atmosphere or whatever, right? There's so many factors, and you said this like this coupling model, so there's all these things that couple together. How do you even like put that into the math? I wouldn't know.
I guess it is very complicated, almost to the point of no one person does it. Climate models go beyond like in some smaller like applications, you can have one person build a model or something. All climate models are basically built by teams of people, and then people will use the same climate model because of this complexity. But we're also very good at figuring out what you can simplify. So what points are not going to be as relevant. Just scaling terms and stuff of, does this affect your scale, like your scales of motion that you're talking about? But the scales of it are so large in climate models because you go from really, really small things like cloud physics, like can have a big impact on cloud formation. So this can be like aerosol interactions and stuff affect cloud formation, which then affect where you have precipitation, where your hydrological pattern looks like, which is on the large scale of like tens of kilometers, but it starts at like micrometers. So what you resolve and how much you parameterize really affects those equations. But they're also like, there's like a set of like 8 like main equations that you use, which are all interconnected with each other, and all your momentum transfer equations and stuff. And yeah, it gets quite involved.
Well, one of the challenge for like climate and weather models is that, you know, it's very chaotic. So I want to ask like, well, what is, well, okay, for the audience, when I say chaotic, I mean they're very sensitive to initial conditions where when a little thing change, you know, if you predict the next day, it might be completely different, right? So how sensitive is your model? Like, or even how accurate is it? Because if you disturb maybe one parameter of one of the equations slightly, it might change the entire dynamics. or is it? Or is it very stable?
Sorry, one quick comment. I know when it comes to fluid mechanics and chaos and weather and things, it's all about scales, like you said, right? So, I mean, for weather, if you're just trying to like you look on your app, the weather report, it's gotten pretty good now, but you can't predict it very well more than a day or two in advance. It starts to get a bit more uncertain. But you can predict weather over long time scales pretty well. You can say like next year is going to be a really dry year with pretty good confidence. So I'm wondering, yeah. So does it?
That's not from equation. That's from statistics, I think.
No. You can get that from equations too. Actually, you can find
But
overall
I
trends.
thought they used
anyway,
like previous year's parameters to compare to what happened, and didn't that guide
That's like
the results too?
very old school method almost of weather prediction, like where you use last year's or previous years. Is like the farmer's almanac method of weather prediction, whereas we actually more now use climate indicators. So you might know it's going to be a really wet year or dry year next year because of like ENSO, because you know these specific water temperatures and you know how these like teleconnections relate. So it's more like a physical understanding close. And that's it. It's the question of scale for how chaotic it is. So we do things to reduce this kind of chaos tendency, but it's higher on weather predictions. It's higher on 2 days, 3 days out, because you're looking at something on a smaller scale too, right? Like you want to know the weather over Edmonton. You want to know the weather in this region, and you want to know if it's going to snow or it's going to rain at 10 a.m. or 6 p.m. You know, like you're on a really short scale. Whereas when you're talking about like a prediction for climate, which is like climate is just like the average of weather over a long time, basically. So that gives you the climate of a region. And that you're talking on a scale of what's going to happen in northern Alberta in the next, over a month or something. Like you're talking on a bigger scale. So then that chaos kind of gets less and less. So that does make a big difference to what you can predict.
I want to add another comment to us. Talk about weather prediction. I remember every year in my country we have a agricultural day where they do weather prediction. The way they do it, we have these sacred cows, and two of them, and we have different food in front of them. We have like liquor, we have I think rice and grain, or grass. It depends on what they eat. Which would predict, are we gonna have much water this year? Or is it going to be drought because they're not eating this thing? It's like, well, people used to believe that, right? Like, and it's like, it's a big deal. Like people showed up, it's a huge event, and these are the cows. Yeah. But now, in retrospect, as a scientist, it's like, damn, that is hilarious.
I'm still a firm believer in Groundhog Day. So,
I mean,
also, do people like sports bet on the cows? Or you're like, oh, I think he's gonna eat this thing.
But it's a sacred event. Just you gotta relax a bit.
Man, so is American football to some people, but like.
So going back to climate models and away from cow modeling, to predict these, I guess, events years in the future, I guess, is what we're concerned with for the Arctic. Are you running this model just once and just kind of taking that result, or do you have to run the model many different times over? What's kind of the process for one, running these models, and two, making sure that they're actually right?
Yeah, so there's kind of two ways you deal with this, and it does depend on your resource availability and what you're trying to figure out, how you do it. So if you are a government, because governments are generally the people who have the resources to run these like 100-year climate predictions or something, you run what's called an ensemble suite. You run the same model, slightly perturbed initial conditions and boundary conditions, many, many times, however many you have the resources for and are able to for however long you're running it. And so then that gives you kind of like an average, the ensemble average. So you kind of deal with some of those variations and the drift in the model over time to come with an average of a prediction of like temperature or precipitation patterns. The other way, which we do more because we do a lot more of like understanding processes and model development and understanding things on a more local scale, is something called hindcast modeling. So you are modeling years that have already happened. So then if you are modeling a year that has already happened, you likely have some observational data to compare to. So you'll take your model, you'll run it for your like 20 or 50-year period or something to look at, what causes these changes, why is this happening? And then you compare with observations at key points where you have them to see if your model is producing accurate results. It's a little more constrained, but obviously you can't do it for the future. But you don't have to run that suite of ensembles, so it's cheaper to do.
Yeah, I actually was thinking about that because the one way to verify it now, because like we have a lot of data for the past, let's say, I don't know, 30 years. So like if you're running 5 years period, you just compare to bunch of 5 years period data in the past. So, I think now in the future, we're going to have much more data to work with to try to create a better predictive model. And interesting, you said ensemble sweep is basically you go into this parameter space and try to sample in a specific way, right? And for the audience, ensemble is basically collection of parameters, and you kind of want to crawl through that to make sure that there's nothing missing that you didn't look at, right? And sometimes it's really hard when you have a lot of parameters. You don't know which one is really more important, really, especially in the long term. So you just have specific where to sample to make sure you take care of the rough edges that you might miss. And I think it's a good way, but I think it's very resource intensive way. Am I correct?
Yeah, I mean, that's the problem of like climate models sometimes by far use the most computational resources in science. I think particle physics is one of the other examples where they use a lot, and there's some chemical, but like we use terabytes of data and run on like, hundreds of nodes and thousands of nodes on big supercomputers because they are very computationally expensive. And so there's a lot of questions that you can't answer without them, but you also have to be cognizant of the cost when you try to answer questions because it takes a lot to run an ensemble. So you want to, before you start getting into the parameter testing space for the future, you want to have a very good idea of the physical conditions now. We can't guarantee that the now is going to be following the same governing equations as the future. If you have enough, changes in forcing, you can change how you can, flip regimes basically. But just getting an idea of how the system operates now and how we expect it to change can help like narrow down those parameter choices. But just the scale questions alone make it really difficult to do because you have to parameterize so many things.
Lately, I've been chatting with a bunch of astronomers in my wing, and I feel like your work is in a way quite similar, the way you have to deal with data, because they try to make models to predict how galaxies and stars work, star formation, dust in the galaxies. And well, we had a Parisa that came in one of our episodes talking about space dust. But astronomers kind of do that in space, right? They have to like be efficient with their resources because like they have to, let's say, put in requests for the specific telescope to look at the sky in a specific time, and there's a lot of data that came out of it, and to process that much data. And I think even in climate modeling, we even have more data because we're not just limited to light from the sky. We have temperature, we have speed of the current, we have anything speed of the wind, and there's so much more equations you could put in rather than just like, well, we had redshift and blue shift of light and bunch of autolights and microwave and well, just light. So and gravitational wave. But I feel like the climate modeling is quite challenging because there's so many parameters. So I think it's gonna be a question on your preference. What are your favorite parameters to work with?
Favorite parameters? I just really like sea ice, man. Love messing around with the sea ice parameters.
What does that mean, the sea ice parameter?
Oh, ice dynamics is very, very complicated. And this is a whole nother PhD, a whole nother research field, just figuring out how ice forms, how ice breaks, how ice moves. Like, because you can think of it as, water freezing, but then it's a collection of water particles frozen together. And it's going to have some elasticity to it. It's going to have some bend to it. It's going to have different dynamics depending on thickness, conditions when it froze, how ridged the ice is. It's very, very complicated, sea ice dynamics. And you can mess around a
Because,
lot
well,
with sea
I
ice
remember in my
parameters.
my undergrad research was actually on water.
Yeah.
And I learned that there's more than like 16 different types of ice on the phase diagrams, right? And I'm not sure how many formed in the ocean because different condition have different ice, and different ice have different, let's say, density,
Yeah.
a different crystal structure, and ice in space has their own thing. And I'm not sure how much of that is affecting the climate or like the weather behavior or even like the current behavior in the ocean.
Oh, it totally is. Like sea ice. So if you can think about, like one good example is the heat transfer from the atmosphere to the ocean. So the atmosphere, heats up, solar income radiation, has long wave radiation. The ocean takes up a lot of that heat currently as it's like that exchange at that boundary. And then that water, which then warms and stuff, and in certain places is able to sink. This is deep convection, which is a really important concept of, heat transfer and carbon capture as well, where you're able to take that surface waters, which have been heated and full of carbon, and sink them down to the deep, sequester them basically. And if you have sea ice at the boundary between the atmosphere and the ocean, this affects all of those heat transfer processes. So if you have air blowing over ice, it's going to be colder than air blowing over the ocean because it's going to pick up cool air from it. And you're also going to have less humidity in this air. So if you're in a coastal area, whether or not there's ice off the coast from you is going to make a big difference to the weather that you feel. And it's also going to make a big difference overall if we have more thin ice, so there's less contact between the atmosphere and the ocean, which is something we're seeing happening with climate change, of where because we've melted this multi-year ice, every winter it refreezes very thin and very broad area, and then it melts again every summer. This change in dynamics changes that heat transfer between the atmosphere and the ocean. The ocean can take up less heat then because it has this barrier in between. So this will change. This is part of what changes with polar amplification as well, as this change in sea ice patterns. So ice makes a really big difference to dynamics.
You sound like you're very more like computational / theoretical side. Have you done any field work on the Arctic stuff, or just you do the more like computer?
I'm very modeling side, but I have been on one research cruise, which was on an icebreaker where we did a transect up the North Atlantic, just taking water samples and CTD, which is how you measure the temperature and salinity going down at depth of the water. It's like this big rosette thing that you drop down, and it measures the conductivity, which tells you the salinity of the water, and the temperature of the water. And you get a profile of the water column. So I did do that once, which was great. And I really enjoyed, but I don't do a lot of field work.
Was it terrifying? I find those like icebreaker ships because like is if something messed up, you're kind of stranded, Like, is there's nothing around except for ice, and it's kind of terrifying thought to think about it. Like,
the one I was on had a helicopter pad.
there was a lot of horror stories of back in the olden days, humans, explorer, navigators try to go up there and they got stuck on ice. There's nothing to eat. They have to resort to cannibalism. It's like, well, I hope that doesn't happen anymore, but.
I was going to say, I think there is, Arctic field work problems sometimes, but they happen less on the ships these days and more on groundwork. Some of that work is a little freaks me out hearing about it. When I hear what people did over their field season, I'm like, oh, okay. On a ship, at least, we had like a helicopter pad and like there was like a cook on board and stuff. I didn't feel very at risk ever. Maybe just seasickness.
Someone I went to high school with became like the chef for an icebreaker boat somewhere in northern Canada. So I'm wondering if that was the ship. I don't know.
Yeah, Canada has 2 icebreakers, so pretty good. They're very expensive. I was on the German one though. So.
Oh, okay.
I want to ask about the icebreaker ship. It's like, how does that work? Because like, can't ice be like very, very thick? Do people just like go break it in? How do you know how that works at all?
Yeah, like a little bit. So it does have to do. You build the ships. They're very steel plated, very thick, and they are very thin and long, so they are able to like go through. Most often they'll do they call it like where you almost like ground on the ice and then the weight of it will go down and break it as you're going through. So you're kind of pushing the ice underneath you and then breaking it from gravity. And there's some complicated like dynamics with it of the way you build the front of the ship and then the torque of it, because you can also like drive in and then turn to like break it because they're very long too. They don't look, you can like tell an icebreaker from a regular ship. They have like a totally different shape and like size.
So,
to them.
but it doesn't like cut out chunk of ice that make it float around, like free the ice out, right? It just like go through like a mole into the ground.
It's the idea. I've
But
seen
it doesn't
them
carve out like pieces of ice off the Arctic.
They I think they just carve out a little path in front of them, and like of course it breaks the ice and it floats around out of their way as they go through it. But I don't think it's like thin ice. It's thin enough that a boat can break it. It's not like these huge Arctic shelves or whatever, right?
I have watched a documentary on icebreakers, and they also have very advanced like sensing systems so that they can tell where the ice is, and they use a whole network of sensing systems to figure out, okay, this is a good place, this is a bad place, and yeah, it's a very advanced topic now.
I have a question about one of your earlier comments, is that this is all for the Arctic. It's all for the northern hemisphere of the Earth. So why don't, and I think you said that you don't see this down south as much, at least yet. So is there a reason for that, or is it just a bunch of reasons?
Yeah, I mean, there's one really good reason. Like, I was talking about polar amplification. We don't see, like, technically the concept of polar amplification should be valid in the North Pole and the South Pole, like, physically. But we haven't seen that manifest really in the South Pole. And there's one, like, really good reason that we think this is. So if you think about the Earth and, like, the currents and wind patterns of the Earth, this is disrupted by the continents, right? So as you know, ocean currents get broken up by the continents. Winds also kind of get broken up and changed by going over land versus ocean. If you think about the South Pole, there's one big landmass like right at the pole, but there's no continents right around it. So you get this, they call it the Antarctic circumpolar current. So it's this really, really strong current that goes all the way around Antarctica. And it breaks up the air masses and water masses of Antarctica versus the rest of the world. And so it keeps it more contained. So Antarctica has seen far less warming than the Arctic, and far less ice loss, far less amplification than this. And it's likely just due to this circumpolar current keeping everything more contained. There's less hot air is able to get in, less cold air is getting out. So there is a lot of research now going into Antarctic climate change because it is such a big uncertainty in the future of how long this effect lasts for. Once it starts melting, you have such a huge ice sheet, which can contribute so much to sea level rise that you want to know, what's going to happen with it in the future. So there's a lot of work going into it and just understanding, what is going to happen and how much warming will it take to start seeing these effects in Antarctica. But it's just a really different scale. Like the Arctic has warmed so much so quickly and is seeing so many extreme effects already. And Antarctica is just starting to catch up in this and just starting to melt even.
Is that why the circulating current around the South Pole, is that part of the reason why there's like no animals down there? Or is it just completely different reason?
I think it is related. Like I think it's just harder for species to get there. But there's stuff, there's penguins and birds, and there is some very cool
polar
fish
bears, right?
down there too. But
no bears.
There's actually a really good Minute Earth video that they just released describing this Antarctic circumpolar current, and how there are different, it's not quite different species, but like if you look at giant squid on one side of the current versus the other, it's that current has kind of locked them in, and a lot of different aquatic animals in, such that they're a little bit different than their, I guess, more northern species folk, however you say that.
How do they know about giant squid when like we haven't barely seen one, right? I think there's only one live video footage of them.
We've seen enough. They wash up when they die.
No,
Oh,
I
yeah.
think you're talking about colossal squid, which is like a bigger than giant squid.
Oh,
The colossal squid, that's the one we actually never seen in real life. We've seen them wash up once or twice, but I think that's one that eats giant squid. That's the one that like goes like really deep. I was
thinking
reading about it. It's interesting.
we keep getting sidetracked, but like I'm thinking of the one that fights sperm whales.
Those are also
I-
giant squid and colossal squid.
Yeah,
They both do that.
Yeah, I'm so interested in those. Like, how
Yeah.
is it? Anyway, enough about that.
I feel like like the Arctic job is like great for Canadian because they're used to the cold, especially like you guys in Edmonton, which somehow snowed in October. Is impressive.
I was gonna say, I always get when people hear I'm studying like oceanography, they're like, "Why are you in Edmonton? That's so landlocked." And then I'm like, "Arctic. It's the closest to the Arctic."
Yeah, people forget that there's this northern here. There's a lot of water, ocean up there.
Mhm.
So I think this is a good time to pivot to your life a bit. So how did you get into physics/computer science out of all programs, right? Like, what motivates you into science?
I did my so I'm the first person in my family to go to university, which I think is the classic story of how you end up in comp sci or engineering, because you're like, get a job out of it kind of thing. So I ended up in computer science in my first year when I got into university, and I did my first year, and I hated it. I was like, oh man, I don't want to work at like a startup and do some like web app or like just work on like, front end user things. I found it really like unmotivating and boring. And I was like, I need out of this. And so then I was like looking around at like, what could I do? Like, I didn't mind the technical side of it. And I liked the idea more of like back end stuff. And so I was looking around and like doing other courses. And I did a physics course, and I was talking to some people, and they were advisors and stuff. And they were like, well, physics is a good combination with computer science because you can do a lot of different modeling applications, whether that's in like just computer modeling in general, like numerical analysis work. And you're doing a little bit more, real applications work, not user side work. And there's a lot of different ways you can go with this. And so I was like, oh, okay, sure, that makes sense to me. I did well in physics in high school, and I, just don't want to work on HTML code for my whole life. So I'll try this. And then I did co-op. We had co-op at my undergrad university, which you would do with computer science, where you would like do work terms. So I did like 4 of those. And the first one I ever got, which was really lucky, was at the Canadian Centre for Climate Modeling and Analysis, which was in Victoria. It's still in Victoria. And just doing some like helping them fix up some scripts to make some little plots of like, oxygen concentrations in the ocean. I thought it was really cool. I was like, oh, this is an application. This is climate change. This is real world. This is like the combination of everything I've been doing, but with something that's like actually interesting. And so then after I did that in my second year, I kind of stayed in that field of just like climate modeling, which is a whole branch of physics, like atmospheric physics and physical oceanography are a whole like different branch of physics, which I started getting into. And then I started working for the government, and then I got connected and ended up here doing Arctic climate change.
So you basically got proselytized into climate field. So I'm gonna walk you back through the memory lane a little bit. So when you were even younger, high school, middle school, or even like grade primary school, were you like a scientifically minded, or like were you more like Liam, for example? He was more bio-ish, right? You like insects and outside and grass and yeah. So were you always like science, or like were you like really into math? What sparked you into the field of science or mathematics, computer engineering, STEM?
For me, just on the comment on insects and stuff. Yeah, I was super into like biology and stuff, and then I realized it was really hard to do, so I went towards physics, which is hard to do, but conceptually you're simplifying things as much as you can when you do physics, right? Like think of one atom, not like a living creature in an environment. Like so anyway, yeah. I'm still waiting for someone to have the same story as me, but our guests so far, they all very different stories, and I think that's a good thing.
I don't have the same story, but I will say as a fun tidbit, this didn't last very long, but when I was like 5 or 6, I was really into ants. Like I thought they were really cool. And so this was when people were starting to ask you, what do you want to be when you're older? And so my dad thought it was really funny to teach me the word entomologist and get me to say to people when they asked what I wanted to be when I was older, say, I want to be an entomologist. I was like 5. That didn't last very long. I wasn't that into biology, but that's as close as I have to that.
I feel like he should tell you a lepidopterist. People study butterflies. That's like, that's your job, to study butterflies.
Yeah, what I wanted to be when I was younger, I wanted to be a journalist for the longest time. I was like always a very, like Englishy, history kind of person, very in the social sciences kind of thing. But I guess it just like, this goes back to, I don't know, like this experience of like first generation, like kids in university, of that was not really like a viable option for me. Like I was paying my way through university. I didn't have anyone who'd done this before. And all that I knew and I'd heard was just, you're not going to make any money being a journalist. You're not going to get a job. You go get, some social science degree and then you work as a barista at Starbucks or something. And so I was like, and I did well in high school, like in overall. Math was never my favorite thing, but it never went poorly for me at all with math. It was just, I never was really interested in it. And I, liked a lot more of the social sciences, but I was like, I was good. I was really good with tech. I'd always gotten really good. Like we did computers courses in high school, and I was like coding when I was a little kid with friends. Like we would make like people's, it wasn't MySpace, but what was it? There was this really old like social media site. It was like a forum site.
Tumblr?
No, it wasn't Tumblr. I don't think it exists anymore. But
I think we're all the same age, so probably the same generation.
It was like, I can't even remember what it was called, but it was really big in my high school. And me and my friends would code people's home pages, like HTML code. So like give different like graphics and music would play and things like that. And so then I was like, well,
kind of like a blog, like a personal blog site.
Yeah, it was like a blog site, but I can't remember for the life of me what it was called.
I know what you're talking about, but I can't remember either.
It was very much like MySpace. Like I think it was a MySpace ripoff.
Yeah, because I think when I grew up, there's a website called High Five, which is like basically MySpace ripoff, because MySpace wasn't popular. High Five was popular, and it's like, so you build your profile, right? And Facebook used to be like that, where you build your profile.
Yeah.
And now it's really different. So that's interesting that it got you into coding. I think that attraction on like logical puzzles is really interesting, because that's what you do now. You solve this very complicated puzzle of how climate models work and how climate or weather manifest, and you try to figure this big puzzle. I can see how your background or like your interest in coding, computer science, scripting comes into play. That's quite neat.
How did you? So I don't think I'm quite a first generation student. I have like aunts and uncles who went to university, but my parents didn't. So I went into it kind of blind, and maybe I had more resources to access, and I just didn't. I should have, but I didn't. So we never had coding options growing up where I was. Like I didn't even know what coding was until my first year of university. I just didn't really understand how computers worked. I was just kind of like, oh, they work. There's some physics going on there somewhere. But I didn't know about coding very much, because there wasn't like coding classes in my schools or anything. There is now that I'm gone. But so how did you like get into that?
Sorry, just to comment, to be fair, you did grow up in rural Nova Scotia, so the odds weren't stacked in your favor.
But I went to like I'm from rural Nova Scotia, but I'm from like the second or third biggest place, maybe fourth in Nova Scotia. So
Remember how you described your middle school to me and,
Well,
and rethink what you're going to say.
true. Sorry, my high school was pretty good. Yeah, my elementary, middle school, maybe not. So but did you get like introduced to coding in school or through your friends, or like how does that even work? Because
We didn't have a computer. My parents are really big hippies. Like they were back in the 90s, like alternative lifestylers. Like that was what they called themselves. They owned like 25 acres in the bush in Australia and like
Oh, wow.
lived off the grid. That was where I was born. Like we didn't have a computer. We didn't have a TV until I was 15. Like I didn't, but my friend had a computer. Like my best friend from like elementary school to high school, like she had a computer and I would go to her house and we would, look up old YouTube videos in like 2008, when they were like still fun. Just kidding.
when they weren't, when they were
like,
just like random
social media, like the forums and stuff and like things like that. Well, that was like my earliest introduction to them was just like her house and her family computer with her like older brother who was like 6 or 7 years older than us, showing us things that were like not age appropriate at all just because he thought it was funny to show 10-year-olds,
Classic.
I think it reminds me of like early days of the internet, where people didn't know what it was. And it's basically used to be just you connect a bunch of computers together to share some information, and you don't know what goes through the pipe, and it is craziness ensues, right? And it reminds me of this story of your very like archetypal like genius movie story that's like, oh yeah, this person's just out of nowhere just found this computer tinker about it tinkering, keep tinkering, and it's like now they're like the best scientists ever. Like there's like not quite Iron Man kind of type of a story. It's just quite interesting that you came from this very like no technology. Now you're basically doing the opposite of hippiness, right?
Oh.
You're doing with computers all day.
Oh, climate change with computers though, right? Like it's the new age, baby.
Yeah.
Like I mean, we did have though in my high school, we had like a technology class. Like it was like an IT class or something it was called. It was like the teacher for it had like a comp sci degree from like the early 2000s or something, and he taught us how to use like Photoshop and like like all the really basic things, and like the early like 2010s or 2012 or so. So I did have that, and that was where like in high school I was like, oh, I was really good at this, and I was like, oh, okay, well, I'll go to school for this. And then I was like, oh man, I don't want to be a comp sci student.
I think courses like that are so important now. Like the fact they start teaching kids coding I think that's huge. I think I had like a computer class in my high school, but it was not like that. Like I don't think anyone teaching in my high school could have managed Photoshop. It like taught me how to type, like how to like hold your hands while you type, and how to like save documents in Excel and stuff like that. It was super basic.
Get your words per minute like count.
Yeah, exactly. You got tested on like how fast you could type, not if you could use an application or some software, which I think is infinitely more useful.
Well, to be fair, it was like that in the past where they teach people how to use the typewriter, right? It's about how fast you type. Anyways, I'm gonna pivot again to instead the past, look towards the future. So this is the question, and we always ask the guest. I guess I always ask the guest, but I think it's been a while since we have guests, or season 5, right? First guest. So it's about your hopes and dreams. So the question is a very loaded question. So this is not like where do you see yourself in 10 years, but what do you hope to be? Who do you hope to be? What are your dreams? Do you plan to be a climate scientist? Do you want to be working on computational work for a while? Like who do you want to be? Who do you see yourself being as, you look inside yourself? Do you see yourself as a climate scientist? Is that what you hope to be?
I mean, yeah, I hope so. I mean, I like a lot of there's a lot of really great international collaborations that we do because climate science is such a diverse and such a complicated field with so many consequences of knowing these things and understanding. And there's so many great institutions in that I would love to continue working in climate science, especially in the Arctic. I really like Arctic work. Just it's such a important for the rest of the globe, and also just for the communities that live there and for the species that are there. So fast changing and uncertain futures, and just physically
Is that
so
because
interesting.
you are like the cold too?
I like
You
the
prefer
cold.
the cold rather than the heat?
I was born in the tropics, man. I don't know if I like the cold.
I mean, Patrick has been working like in Costa Rica, and so it seems you enjoyed it, right? But you also live in Edmonton. So.
There's something to be said about the cold and preserving it.
Yeah, exactly.
Yeah, so it might tie into your hopes and dreams. I don't know, but I'm wondering, the models that you do, the science that you do you think? I mean, science isn't what it used to be. It's not like one person comes along and does something and it changes everything. I mean, maybe that happens once in a while, but my question is, like, do you think the models that your group's working on and the kind of science you're doing, do you think it's gonna make a big impact in the future? So I guess the goal is, like, you want to convince people to change our ways so that we stop global warming and we stop the Arctic from melting away and eventually the South Pole. Is part of your goal to, like, use your work to try and help convince the world about that, or is it gonna teach us something that we need to change, or I don't know?
I think, okay, I've really avoided being the pessimistic climate scientist for all of this. I've been so good. But I'm going to be the pessimistic climate scientist of, I think we are well past the point of stopping climate change. Like, that would require undoing the past already at this point. Climate change is baked in. Global warming is baked in at this point. But we do have tipping points within that, you know, if you stay under 2 degrees warming, which isn't likely, but you know, if we did stay under 2 degrees warming, you're less likely to hit a lot of tipping points. If you stay under 4 degrees warming, you're still less likely to hit a lot of tipping points. And there's more than just stopping climate change, because it's not even these days a task of convincing people. Like, if you talk to like anyone, hardly anyone at all anymore is like, climate change isn't real. Like, that was like a talking point maybe 10 years ago, but now it's gone beyond that to just, well, what can we even do about it? Or what does that even matter? Or like, how does this, you know, like, okay, it's getting warmer, whatever. But it's more complicated than just warming. It's shifting weather patterns. It's shifting nutrient availability in the ocean, which shifts fishing grounds, which shifts food availability. It's drought patterns. It's sea level rise. It's like coastal dynamics. And so not just stopping climate change, but real physical tools that help people adapt to these changes. We are going to have a fast-changing climate for the rest of our lifetimes, and likely for many generations to come, even if we stopped emissions tomorrow. Like, things are still changing really fast. And just being able to understand what's happening, how that's going to manifest, and how do we adapt to this in a way that like saves people's lives, not that personally, but just as a field. You know, how do we figure out what's going to happen in coastal areas, what's going to happen with food availability and water availability? Like, these are more of the questions we want to answer, and more of like service that climate science can give to people beyond just like climate change is happening. Like, you know, climate science has been saying that for decades now, and what did that do?
Yeah, I guess when I mean like convince people, I mean governments and people with lots of money to try and change the fundamental way humanity does things, so that we, again, like, it's already happening. There's different tipping points. It's just a matter of severity and how can we make it less severe, and also how can we deal with what's going to happen. So,
and how can we know what's going to happen too? Some of these questions can't be answered except for models and calibrated through observations, which we do not have enough of, and in general don't have enough resources towards.
Yeah, I feel like we are going a little bit of a cataclysmic path, but I think I like the key point that you made, that is about for us to adapt, right? If we can't stop it. But humans, I think, as humankind, is very resilient, and we are not that weak in terms of as a species. So I think we can adapt. I mean, we have people like you who are on the forefront, hopefully, right? On like figuring out what's going on, so you can inform other people. Well, maybe you should adapt to it. Maybe we should do this to preserve this thing, or maybe you should change what we do so that we, as a species, not just a one person, right, survive. I think it's a very noble thing. So, well, I think we have talked for quite some time, right? So, well, where should we go next, Patrick?
Well, if you're listening to this, the next place that you can go is on our social media, Instagram. We are at the Hyperthesis. You can find posts about when we are posting episodes. We will have a post for Tahya up announcing her episode. We also provide updates when we are taking breaks, as well as memes, which I haven't seen in a while. So, Liam,
Sorry.
you can also contact us through Instagram, or you can contact us through email. We are hyperthesispodcast@gmail.com. You can send us an email if you have any comments about an episode or questions or topics you would like us to discuss, or if you are an expert in your field. We would love to have you on as a guest, just like Tahya today. So feel free to reach out through any of those means.
So if someone have questions or for Tahya, or get inspired by your story, would you like them to contact you? If so, how?
Yeah, for sure. I'm always love to talk about climate change and the Arctic and models. Yeah, I can email, or I'm on Instagram as well. Weiss-Gibb, WEISSGIB @ualberta.ca.
So, well, I think we can put some of your information into the description if someone interested in your work, or maybe an aspiring young scientist who wants to get into climate science and modeling, or even a young child. Who knows? Maybe you inspire a lot of people. So,
And finally, if you are listening to us, then congratulations, you found us somehow. But we are on Google Podcast, Apple Podcast, Audible, pretty much wherever you get your podcasts. So if you want to share today's episode, feel free to share it through any podcasting service. We are based out of Spotify. And yeah, and if you have any questions, feel free to contact us or contact Tahya directly. So to wrap up our episode today, we have a story which was referenced to earlier from Pheely.
all right. So since we talked about the Arctic today, I thought long and hard about what should I talk about in terms to the story, but it's not exactly a story. So today we're gonna be talking about polar bears, because who doesn't like bears? So what about polar bears? Polar bears is actually one of the most predatory animal live on the planet, right? Because there's nothing to eat up there, so they have to be very, very aggressive. So the polar bear, some facts. A male Ursus maritimus. I think Ursus mean bear, maritimus like the maritime. The maritime bear, the largest member of the bear family, can stand more than 3 meters tall on its highest leg and weigh more than 600 kilograms and can age up to 30 years. So this information, I get all of this from the Canadian Geographics. So you can find the source later. A female can give birth every 3 years to usually twins, which will stay with the mother for the next 2 years. And the diet, they actually eat this primarily the skin and bubbler of seals. So they eat seals a lot. They hunt seals using the sense of smell and a lot of patience, tracking down layers and wait hours and hours for it to surface at the breathing hole, and just basically snatch it out of the ocean with their claws. And then occasionally they will attack human beings who dare go around their territory. Then they're not known for their subtlety. They just go at you and try to stop them. Is there, like I said, up to 600 kilograms? That's like a car. Anyways, there are around Actually, there are 19 subpopulations of polar bears in the world. Actually, 13 of them are found in Canada. So most of them are actually found in Canada. Around 2/3 of the world's polar bear population live in Canada. And research actually from 1984 to 2004 showed that like one of the subpopulation, the Western Hudson Bay, it, has declined from around 1,200 to 900. And the trend line from the study suggests that the population would fall by 2011 to as low as around 700. So that could be concerning. And the way scientists actually count and study polar bears, there are two ways. First is to capture and recapture. Second is to aerial survey, maybe sending some planes, drones. The capture and recapture is actually quite dangerous because you have the researcher has to be close proximity to the bear. And as I said, they're very aggressive bears. But it's a more involved. You can get more samples. You can take skin and blood samples, measuring the weight, use ear tags to identify the country of capture. On the other hand, the aerial survey, they use helicopters to count bears along the predetermined line. It's quite tricky because even it's visual, but polar bears are white, so it's snow and ice, so they can camouflage really well and blend in with ice, and their dens and ridges can be their dens can be camouflaged behind ridges, and it can be missed. And it can be very difficult to work with polar bears because they can range across international boundaries. They just walk and run over hundreds of kilometers of ice and frigid open water. They can dig into dens and camouflage themselves on snow fields. The recapture and recapture studies where bears are tranquilized are quite problematic. Well, first of all, drugging animals are quite dangerous. Even though you can do it quite safely, there are always a risk associated with drugging animals or tranquilizing them. And in fact, when we talk about polar bears, we like to think of them as a single species group. They are polar bears. But the truth that the success or failure of, let's say, a single subpopulation might have a wide range of fluctuations that could say very little about the health of the other. Let's say if you think about one group is declining, it say very little about the other group if it maybe they're flourishing. So despite all this, the numbers still tell a story. It's not really clear though what the story is because let's say in Davis Strait between Greenland and Baffin Island, the polar bear population actually grew from 900 animals in late 1980s to around 2,100. In Hudson Bay, northern Hudson Bay, is estimated to be 2,300, but now stands around 2,500. So there are actually quite of the variance between each subpopulation. And one study actually predicted 40 to 70% of pregnant female could fail to deliver healthy cubs if ice breakup happens 1 month earlier in the 90s. But polar bears are quite long-lived animal, but they reproduce quite slowly. So counting numbers of animals that are alive today might not really paint an accurate picture of what's going on. And some research also observed that the number of cubs, let's say in the Western Hudson Bay, is dramatically lower than in the past. Well, but maybe that doesn't tell the whole picture, right? And this complexity that arises from the variance in subpopulation, that maybe they're stable or rising, or there's overabundance of bear, that could also lead to competition for food because, like we said, the food is quite scarce. And the health of the entire population depends on many factors. And in this way, limited hunting could even improve the overall health to calm down a little bit. So my point to the whole thing is there are people that say polar bear are declining they are going away, but there's also authors study that say they are rising up. And most of the time when we encounter these type of conflicting stories, the truth usually lie in between, right? So maybe part of it are declining, part of it is increasing. What is actual story requires much more in-depth research and survey, and there are a lot of influence from humans too. So all in all, we are not really sure. So I hope in the future, with people who are working incredibly hard to study polar bears and the Arctic, can figure it out and see what we can do about it. So that is the story for today.
Well, thank you very much, Pheely, for that riveting story on polar bears. And I mean, there's a lot that we can learn about them, and maybe Tahya's research can influence polar bear conservation projects. So, to end the episode, thank you very much, Tahya, for joining us for this episode. And just, do you have any final words?
No, thank you so much for having me. It's been fun.
Yeah, thank you for coming.
Yes, thank you.
And just a little rhyme that we learned in school, because I grew up further north. It's, if it's black, fight back. If it's brown, lay down. And if it's white, good night.
Really? You'd rather fight a grizzly bear than a polar bear?
No, it's a black bear that you fight.
No, I'd rather fight a black bear than a grizzly bear. But would you rather fight a grizzly bear or a polar bear?
Oh, grizzly bear, 100%.
Yeah, grizzly.
Oh, really? Okay.
Polar
Jeez.
bears
Polar
are
bear is
massive.
the worst. It's like the worst of all, because like they say, black bear you want to try to be big, right, to scare it away a
I'm
little
not
bit.
talking about
Brown
black
bear,
bears.
you're not really have a good chance, but the polar bear you really have no chance.
That's true. I guess especially if you're in the Arctic.
And polar bear they torture you too. They just like nibble you.
One thing on polar bears, of one of our problems with recovering, we put moorings in the water in the Arctic. And sometimes you don't get to recover them because a polar bear during the winter when the sea ice was there came and pulled the whole thing up and chewed it out. So polar bear damage to equipment is like a real cost sunk in the Arctic.
Who knew?
Well, with that in mind, thank you again for joining us, Tahya. And thank you all for listening. Bye, everyone.
Take care.
See ya.
Bye.